Before Earth existed, before oceans, continents, or even the sun itself, there was only a cold, silent cloud drifting through interstellar space. But something disturbed it, and from that disturbance, an entire planetary system would be born. Around 4.6 billion years ago, our story begins inside a vast molecular cloud, composed primarily of hydrogen and helium, the oldest elements in the universe. But this was not empty gas. Mixed within it were heavier elements: carbon, oxygen, iron, forged in ancient stars and scattered by supernova explosions long before the solar system existed. These elements would become the raw material of planets, including Earth. Then, a trigger, possibly a nearby supernova shockwave. It sent ripples through the cloud, destabilizing it. Gravity takes over. At this moment, everything changes. The cloud begins to collapse inward under its own gravity. As it contracts, it doesn't fall evenly. It spins faster and faster. This is the fundamental law of angular momentum. As the cloud shrinks, its rotation accelerates. Imagine a spinning ice skater pulling in their arms. The same physics applies on a cosmic scale. As collapse continues, two forces begin to compete: gravity pulling inward, rotation pushing outward. The result is inevitable. The cloud flattens into a vast rotating disk known as a protoplanetary disk. At its center, matter begins to concentrate. Temperature rises, pressure increases, and deep within this growing core, a star is forming. At the center of the disk, the proto-sun ignites, not yet through nuclear fusion, but as a T-Tauri star, a young, unstable phase of stellar evolution. It shines fiercely, it emits powerful solar winds, and it begins to dominate everything around it. Eventually, as pressure and temperature reach critical thresholds, hydrogen nuclei begin to fuse into helium. The sun is born. But the sun is only part of the story. Around it, within the swirling disk, something equally important is happening. Tiny dust grains, microscopic particles of rock and metal, begin to collide. At first, these collisions are gentle. They stick, clump, grow, millimeter by millimeter, centimeter by centimeter. Over time, these grains form larger bodies known as planetesimals, some reaching kilometers in size. Then gravity takes control again. Larger bodies pull in smaller ones. Collisions become more violent. Acceleration grows. This is runaway accretion. Within a relatively short time, perhaps just a few million years, these bodies evolve into protoplanets, the early versions of worlds. At this stage, the solar system is no longer a cloud. It is a battlefield. Countless protoplanets orbit the newborn sun, colliding, merging, and reshaping one another in a chaotic gravitational dance. Some will be destroyed, others will grow. One of them will become Earth. But the Earth that emerges from this chaos will not be the stable world we know today. It will be molten, violent, and constantly under attack, because the process of formation has only just begun.
The solar system is no longer forming in silence. It has become unstable, violent, unpredictable. Around the young sun, countless protoplanets now compete for dominance, and among them, one begins to stand out. At this stage, size becomes power. The larger a body grows, the stronger its gravity becomes, pulling in more material, faster and more efficiently. This is known as runaway accretion. Imagine a snowball rolling downhill. At first, it grows slowly, but as it gets larger, it gathers more snow with every turn, accelerating its own growth. The same principle now unfolds in space. Dust became rocks, rocks became planetesimals, and now planetesimals merge into something far more massive, a growing world, the proto-Earth.
But this growth is not gentle. It is defined by collision. Every orbit is unstable. Every encounter carries the potential for impact. Bodies collide at tens of thousands of kilometers per hour, releasing unimaginable energy. Some impacts add mass, others tear material away. Fragments scatter only to be pulled back again by gravity. Nothing is stable. Nothing is safe. This is planetary construction at its most violent. At this moment, destruction and creation are the same process. Each collision delivers kinetic energy directly into the growing planet. Rock melts, surfaces vaporize, shock waves ripple through the forming world. With every impact, the proto-Earth becomes hotter, denser, more dynamic. This is not a solid planet. It is a partially molten, constantly reshaped mass of rock and metal. And yet, despite the chaos, this process is astonishingly fast. Evidence suggests that Earth reached most of its mass within 10 to 20 million years, and possibly even as quickly as 3 million years. On a cosmic scale, this is almost instantaneous. In less time than it takes continents to shift today, an entire planet takes shape. But collisions are only part of the story. As material accumulates, gravity compresses the interior of the proto-Earth. Pressure increases toward the center. Atoms are forced closer together, and this compression generates heat. At the same time, radioactive elements begin to decay. Impacts continue to inject energy. Together, these processes transform the young Earth into a heat engine. Its interior grows hotter and hotter until large portions of the planet begin to melt. At this moment, the proto-Earth crosses a critical threshold. It is no longer just growing, it is transforming. The increasing heat will soon trigger one of the most important processes in planetary history, a complete internal reorganization of the planet itself. Because inside this molten world, something is about to separate. Heavy elements will sink, lighter materials will rise, and in doing so, Earth will build its internal structure, the foundation of everything that follows.
The young Earth is no longer just growing, it is overheating. Every collision, every compression, every radioactive decay reaction is pushing the planet toward a critical threshold, a point where solid rock can no longer remain solid. Earth begins to transform. It becomes a global magma ocean. Its surface is no longer land, but molten rock. Its interior is no longer stable, but churning with heat and motion. Temperatures rise into the thousands of degrees. Impacts continue to strike, remelting any regions that begin to cool. There are no continents, no oceans, no atmosphere as we know it. Only a glowing, turbulent world, reshaped continuously from within. And within this molten chaos, a profound transformation begins, not driven by impacts, but by gravity. Deep inside the magma ocean, materials begin to separate by density. Heavy elements, primarily iron and nickel, start to sink, pulled relentlessly toward the center. This is the iron catastrophe. Like droplets of metal falling through an ocean of liquid rock, they descend, deeper and deeper, merging into a growing central mass. At the same time, lighter materials, silicates, are pushed upward, a planetary sorting process unfolding on a global scale. As the iron sinks, it begins to accumulate at the center, forming Earth's metallic core. This transformation happens rapidly, within about 10 million years, and it releases enormous energy. As dense metals fall inward, gravitational energy converts into heat, melting the planet even further from within. The deeper the iron sinks, the hotter Earth becomes. Above this forming core, lighter silicate material begins to stabilize. This becomes the mantle, a vast semi-molten layer
that will make up most of the planet. But it is not still. It moves. Hot material rises, cooler material sinks. Even now, Earth's internal engine is beginning to take shape. For the first time, the planet develops a layered structure, a dense metallic core at the center, a massive silicate mantle above it, and eventually a thin outer crust, forming as cooling continues. This structure is not just a feature, it defines Earth's future. Volcanism, tectonics, surface evolution, all of it begins here. And deep within the newly formed core, another process begins. The outer core remains liquid. Molten iron moves, driven by heat and planetary rotation. This motion generates electric currents, and those currents create a magnetic field, a planetary shield, invisible but essential. Without it, solar radiation would strip away the atmosphere. But for now, this field is only beginning to emerge, a byproduct of a still-forming world. By this stage, Earth is no longer a loose collection of debris. It is a differentiated planet, structured, dynamic, and still unstable. Because while its interior is beginning to organize, its exterior is about to face one of the most violent events in its history. A collision so powerful, it will reshape the planet, tear material into space, and create something entirely new. Earth's only natural satellite, the Moon. Earth is now a structured planet, with a core, a mantle, and a surface still glowing with heat. But the solar system is not yet stable, far from it. Protoplanets continue to cross unstable orbits, and sooner or later, two worlds are destined to collide. Somewhere in the inner solar system, a protoplanet begins to form, roughly the size of Mars. Scientists call it Theia. For millions of years, it shares a similar orbit with the young Earth, a delicate gravitational balance, temporary, fragile. Then something changes, a small perturbation, a subtle shift in trajectory, and suddenly, Theia is no longer stable. It is on a collision course with Earth. At that moment, everything changes. Theia strikes the proto-Earth, not head-on, but at a glancing angle. The energy released is almost unimaginable, more than 100 million times greater than the impact that ended the age of dinosaurs. Rock does not simply fracture, it vaporizes. Entire regions of both bodies melt instantly. Shock waves surge through the planet, reshaping its internal structure. The surface is erased and rebuilt in moments. This is not just an impact, it is a planetary-scale transformation. The impact tears vast amounts of material from Earth's outer layers, mantle and crust, and hurls it into space. But this material does not escape entirely. Earth's gravity pulls it back, and around the planet, a ring begins to form, a dense cloud of molten rock and vapor circling at immense speed. Once again, gravity takes control. Within this debris field, particles collide, merge, and begin to come together. Unlike the slow formation of planets, this process happens rapidly. Within weeks to years, the debris gathers into a single growing body. A sphere begins to form. The Moon is born. At this stage, it orbits far closer to Earth than it does today, looming enormous in the sky, dominating the horizon. This idea is not speculation. It is supported by strong scientific evidence. Rocks brought back during the Apollo missions show that Earth and Moon share nearly identical oxygen isotope ratios, a clear sign of a common origin. The Moon is also unusually low in metal. It lacks a large iron core, unlike Earth. This matches the idea that it formed primarily from Earth's outer layers, not its center. All of this points to a single conclusion. The Moon was not captured, it was created. The Earth that emerges from this collision is no longer the same world. Its surface is once again molten. Its rotation may have changed, its axial tilt possibly altered forever. And now it has a companion, a gravitational partner that will shape tides, stabilize rotation, and influence the planet's future evolution. But even after this colossal event, Earth is still not stable. Its surface remains a molten ocean, its skies are filled with vapor and debris, and impacts have not yet ended, because the young solar system is entering one of its most violent eras, a time of relentless bombardment that will reshape the surface of every world.
The Moon has formed, the debris has settled, but Earth is far from calm. In fact, it is entering one of the most violent periods in its entire history. This is the Hadean Eon, a name derived from Hades, the underworld, and for good reason. At this stage, Earth is not a blue planet. It is a world of fire. Volcanism dominates the surface. Massive eruptions pour out molten rock, reshaping the landscape again and again. Beneath the surface, heat from earlier impacts and ongoing radioactive decay drives intense geothermal activity. The mantle churns violently. Magma rises. Nothing remains still for long. If you could stand on Earth at this time, you wouldn't, because there is no stable ground to stand on. Any crust that begins to form is quickly destroyed, remelted by internal heat, torn apart by tectonic forces, or shattered by incoming impacts. The surface is in constant flux. Solid rock forms, then disappears, again and again. A continuous cycle of creation and destruction with no permanence. Then, another escalation. Between about 4.1 and 3.8 billion years ago, the inner solar system experiences a surge in impacts, a period known as the Late Heavy Bombardment. Asteroids and debris rain down on Earth in staggering numbers. Some are small, others are large enough to melt entire regions of the crust. Each impact releases immense energy, vaporizing rock, triggering global shock waves, and reheating the surface. This is not occasional destruction. It is constant, relentless. Now look upward. The sky reflects the chaos below. The Moon hangs much closer than it does today, larger, brighter, and dominating the sky. Debris from impacts streak overhead. Volcanic gases fill the atmosphere. The air is thick with water vapor, carbon dioxide, and other gases. Sunlight struggles to break through. There are no blue skies, only a dim orange glow. At this stage, Earth has no permanent surface, no continents, no stable oceans. Even if liquid water appears briefly, it is quickly vaporized again by heat and by impacts. The idea of a stable planet still does not exist. But this chaos cannot last forever. Over time, the rate of impacts begins to decline. The internal heat, though still immense, slowly starts to fade. And for the first time in Earth's history, Earth begins to cool. Because from this inferno, something unexpected will emerge. A solid surface, the first continents, and eventually, water that will remain. The foundation of a habitable world is about to take shape.
For millions of years, Earth has been defined by chaos, fire, impacts, and constant destruction. But now, something begins to change. Not suddenly, not gently, but inevitably. As the rate of impact slowly declines, Earth begins to lose heat to space. The surface, once a global ocean of magma, starts to cool. At first, only for brief moments. Thin layers of solid rock form, then fracture, then melt again. But over time, these solid intervals begin to last longer. The balance is shifting. Between about 4.4 and 4.0 billion years ago, a critical milestone is reached. For the first time, Earth develops a persistent solid crust. This crust is not like the continents we know today. It is thin, dark, basaltic in composition, similar to modern oceanic crust. And it is fragile, constantly broken and recycled by the still active interior below. Yet despite its instability, it marks a turning point. Earth now has a surface. But this surface does not remain still. Beneath it, the mantle is far hotter than it is today, driving intense convection. Heat rises, cooler material sinks, and this motion fractures the crust into pieces. Early tectonic plates begin to form, smaller, thinner, and far more dynamic than modern plates. They move faster, collide more often, and are recycled more rapidly. Subduction zones are widespread. This is plate tectonics in its most aggressive form. Within this unstable system, something new begins to emerge. Not all crust behaves the same way. Some regions undergo partial melting. Lighter materials, rich in silica, separate from denser rock and begin to rise. Over time, they accumulate into thicker, more buoyant masses. These are the first cratons, the earliest cores of continents. Unlike the surrounding crust, they resist subduction, they float, and they endure. These early land masses are not continents as we know them. They are small, scattered, isolated within vast expanses of newly formed crust. But they are stable. For the first time, Earth has regions that can persist for hundreds of millions, even billions of years. The seeds of future continents have been planted. Even now, nothing is fully settled. Most of the early crust is continuously destroyed and replaced. Very little of this original surface survives today. What remains are fragments, ancient rocks that preserve clues to this early world. Clues locked within cratons that still exist beneath modern continents. With a solid surface now forming, Earth reaches another critical threshold. Because now, something new becomes possible. Because now, something new becomes possible. Water can accumulate, gases can settle, and for the first time, the surface, atmosphere, and interior begin to interact. Because as the planet continues to cool, the skies above it begin to change. Volcanoes fill the atmosphere with gas. Clouds begin to form, and rain begins to fall. For the first time in Earth's history, the oceans are about to be born. A solid surface now exists. The first crust has formed, unstable but real. And with it, Earth enters a new stage. Because a planet with a surface can finally hold something above it, an atmosphere. But Earth's first atmosphere does not last. In its earliest phase, the young planet captures light gases from the surrounding solar nebula, primarily hydrogen and helium. For a brief time, Earth resembles a gas-rich world, but it cannot hold on to it. The young sun, still highly active, releases powerful solar winds. At the same time, Earth's gravity is not yet strong enough, and its temperature is too high to retain these lightweight gases. Gradually, they escape into space. The first atmosphere is lost. Then, a second atmosphere begins to form, not from space, but from within. Deep beneath the crust, the mantle remains intensely hot. Volcanic eruptions dominate the surface, and with every eruption,
gases are released: water vapor, carbon dioxide, nitrogen, and trace compounds. This process is known as volcanic outgassing. Over millions of years, these gases accumulate. A new atmosphere takes shape. But this atmosphere is nothing like the one we breathe today. There is no oxygen, no ozone layer, no protection from ultraviolet radiation. Instead, the sky is dense, hot, and chemically reactive, rich in greenhouse gases and volcanic emissions. There are no blue skies, only a thick, hazy atmosphere, perhaps tinted orange by methane and other gases. And yet, despite the faint young sun, dimmer than it is today, Earth does not freeze. It remains warm, even hot, because of the greenhouse effect. Carbon dioxide and other gases trap heat in the atmosphere, preventing it from escaping into space. This insulation is essential. Without it, early Earth might have frozen. Instead, the planet maintains temperatures high enough for the next transformation. Now, something new begins. The atmosphere no longer exists in isolation. It begins to interact with the surface. Volcanic gases rise, cooling begins, pressure builds, and high above the planet, clouds start to form. The atmosphere is now thick with water vapor. The surface continues to cool. The conditions are almost ready. All that remains is for the temperature to fall just a little further. Because when it does, the sky will open. And for the first time in Earth's history, it will rain. Not for days, not for years, but for millions of years. And from that rain, the oceans will emerge.
The atmosphere has formed, dense, hot, saturated with water vapor. Above the cooling surface of Earth, clouds begin to gather, thick, global, and heavy with moisture. The stage is set. As temperatures continue to fall, a critical threshold is reached. Water vapor begins to condense. Clouds grow darker, denser, until gravity takes over. And then it begins to rain. But this is not rain as we know it. It is continuous, relentless, global. For millions of years, water falls from the sky onto the hot surface below. Steam rises as droplets strike warm rock. Some water evaporates instantly, but over time, more remains than is lost. Slowly, the balance begins to shift. Pools begin to form, basins start to fill, and the first stable bodies of liquid water appear. As rainfall continues, these bodies expand. Small pools merge into larger seas. Seas merge into vast, interconnected basins, until eventually, Earth's first oceans take shape. Evidence suggests this may have happened as early as 4.4 billion years ago. Remarkably, liquid water may have existed even while the planet was still recovering from its most violent phase. But rainfall alone may not explain everything. Some of Earth's water likely came from beyond the planet. During accretion and bombardment, water-rich bodies, asteroids from the outer belt, and possibly comets from the distant solar system delivered additional material. On impact, this material vaporized and later condensed into liquid water, adding to the growing oceans. With the arrival of liquid water, Earth undergoes a fundamental transformation. The surface begins to stabilize. Water interacts with rock, eroding it, transporting sediments, and initiating the first chemical cycles. For the first time, Earth is no longer just a geological system. It becomes a dynamic, interconnected planet, where atmosphere, surface, and interior all influence one another. And yet, there is a mystery. At this time, the sun is significantly dimmer, about 30% less luminous than it is today. By simple physics, Earth should be frozen, but it isn't. The oceans remain liquid. The answer lies in the atmosphere. Greenhouse gases like carbon dioxide and methane trap heat, preventing it from escaping into space, maintaining temperatures high enough for water to persist. A delicate balance, but a crucial one. Now, for the first time, Earth possesses the essential components of a habitable world: a solid crust, a thick atmosphere, and stable, long-lasting oceans. But stability is still fragile. The system is still evolving. Because beneath these early oceans and within this unstable world, something unexpected may soon begin. Simple chemistry will take its first steps towards life. And the question is no longer just how Earth formed, but how it became alive. The oceans have formed. Rain has fallen for millions of years. The surface has cooled. Water now covers vast regions of the planet. For the first time, Earth begins to resemble a world. But beneath this appearance, the transformation is still underway. As heat continues to escape into space, the planet reaches a new threshold. The crust, once fragile, constantly destroyed, begins to stabilize. Not completely, not permanently, but enough to persist. Large regions of solid rock now survive long enough to form a continuous surface. The cycle of melting and destruction slows. The planet no longer resets itself with every major event. Instead, it begins to retain its structure. At the same time, the oceans deepen and become more stable. Water is no longer temporary. It no longer disappears back into vapor after each impact or eruption. It remains. A global hydrosphere is now established, interconnected bodies of water covering much of the planet. These oceans begin to regulate Earth's temperature. They absorb heat, they redistribute energy, they stabilize surface conditions. For the first time, Earth gains a buffering system against extreme change. Now, something fundamentally new begins. The atmosphere and the oceans start to interact. Carbon dioxide dissolves into seawater. Water evaporates and returns as rain. Chemical reactions begin between ocean and crust. This marks the beginning of Earth's first global cycles: the early carbon cycle, the water cycle, and primitive climate regulation. The planet is no longer just cooling, it is becoming self-regulating. Step by step, Earth transforms from a molten body to a fractured surface to a planet with interacting systems. A solid crust above, a dynamic mantle below, oceans covering the surface, an atmosphere surrounding it, each layer connected, each influencing the others. This is the moment Earth becomes a structured planet. But this stability is not absolute. Volcanism continues to reshape the surface. Tectonic forces remain active beneath it. Impacts, though less frequent, have not entirely ceased. Earth is stable enough to evolve, but not yet calm. And within this evolving system, something remarkable becomes possible. The oceans provide a medium. The atmosphere provides chemicals. Energy flows through the planet, from the sun, and from deep within Earth itself. All the essential ingredients are now in place. Because in this newly stabilized world, chemistry begins to organize. Molecules combine, systems emerge, and somewhere, perhaps deep beneath the oceans,
the first traces of life are about to appear.
Earth has changed. From chaos to structure. From fire to water. From instability to a world capable of sustaining long-term processes. But one presence still dominates its skies. A silent companion born from catastrophe. The moon is not a distant object, not yet. It orbits far closer to Earth than it does today, looming massive in the sky, its gravity exerting a powerful influence. Its origin was violent. Its effects are lasting. What began as a collision has become a partnership. Now, the moon begins to shape Earth in ways that are not immediately visible. Its gravity pulls on the oceans, stretching them, lifting them, redistributing water across the planet. The first tides emerge. But these are not the gentle tides we see today. They are far more extreme. Because the moon is closer, its gravitational pull is stronger, raising massive tidal bulges that rise and fall across the young oceans. These movements stir the seas, mix chemicals, and reshape early coastlines. For the first time, a rhythm is introduced into the system, a repeating pattern in a once chaotic world. The moon also shapes something even more subtle, but far more profound. It stabilizes Earth's rotation. Without the moon, Earth's axial tilt could shift dramatically over time, leading to extreme and unpredictable climates. But the moon acts as a gravitational anchor. It dampens these variations. It keeps the planet's tilt relatively stable, and in doing so, it creates long-term environmental consistency, a condition that will shape the future of the planet. At this stage, Earth is no longer evolving alone. It has become part of a two-body system, Earth and Moon, bound together by gravity. The Moon influences ocean dynamics, planetary rotation, and internal energy distribution. Its presence is not incidental, it is foundational. But to fully understand this relationship, we must go back to the moment of impact, back to the collision that made all of this possible. Because the moon is not just a satellite, it is the result of one of the most violent events in planetary history. In the next episode, we return to that moment, to the collision between worlds, to the birth of the moon itself, and to the question that still drives scientific investigation today: how a single impact reshaped the destiny of an entire planet.